In this video, you will learn about angles and arcs. So to begin, let's talk about angles. Now an angle by definition is formed by rotating a given ray about its endpoint to some terminal position. So what that means is, say here you have a ray, here's your endpoint, here's your ray. We can rotate this ray in any direction. So if we rotate it this way, for example, it's going to take us to another location, such as right here, and that would give you a second ray. So that second ray would be the terminal position. So this original ray would be right here. That's what we started with. That's the initial side of the angle. And then the terminal ray would be this side over here. So this side over here that we ended on. So this would be the terminal ray. And then this common endpoint is called the vertex. Now with angles, there's different types of angles. We have positive and we have negative angles. Positive angle is measured counterclockwise. So that would be an angle, if you start here, for example, and you go in this direction, that's counterclockwise, that would be a positive angle. As opposed to a negative angle, that would be if you start here and you go down this way. So if you go down this way in the clockwise direction, that would be a negative angle measure. So when you're working with measures of angles, a degree is one way to measure an angle. So a degree is the measure of an angle formed by rotating a ray 1/360th of a complete revolution. All right, because there's 360 degrees in a circle, right? To go all the way around, it's 360 degrees. 1 degree would be 1/360th of that. All right, so 1 degree would be right there. All right, now different types of angles that we may have are determined by the degree measure. So for example, a straight angle is exactly 180 degrees. That would be something like this right here. That would be 180 degrees. We have a right angle, would be 90 degrees. So that would be something like this right here. So that would be 90 degrees. And then we have an acute angle, it's between 0 and 90. That'd be something like this. And then an obtuse angle is between 90 and 180 degrees, so something like this. Now when you are measuring degrees, measuring angles in degrees on a coordinate plane, okay, we have what's called the standard position, which is where the vertex is at the origin and the initial ray is on the positive x-axis. All right, so for example, if this was your coordinate plane right here, this is the origin, all right, and the angle in standard position would have one ray right here at 0 degrees, then the other ray would be somewhere like this, and that would give you an angle in standard position. So again, we need the vertex at the origin, and then your initial ray being on the x-axis right here. Now, another thing dealing with angles is we have what's called complementary angles. And these are two angles that add up to 90 degrees. So for example, if you had a, let's say, 40-degree angle and a 50-degree angle, you add those together, that gives you 90 degrees or a right angle. So those angles we would say are complementary. And then we have supplementary angles. There are two positive angles that add up to 180 degrees. So if we had a 40-degree angle, something maybe like this, add that with a 140-degree angle like this, together it equals 180, a straight line, so those would be supplementary. Now we can find the complement and the supplement of an angle by using that information that we just gave you. So if you're told to find the complement and supplement of a 35-degree angle, okay, the complement would be the angle that adds with 35 degrees to give you 90 degrees. So some number plus 35 equals 90. We can solve this by subtracting 35 from 90, and that gives you 55 degrees. Now the supplement would be the angle that adds with the 35-degree angle to equal 180 degrees. So something plus 35 equals 180. Subtract 35 from 180. That gives you 145 degrees for the supplement. Now what if you were told to find the complement and supplement of 135 degrees? So the complement would have to add with this to equal 90, but it's got to be a positive angle. So this would have no complement because no positive number can add with 135 to equal 90. but it would have a supplement. It would have an angle that would add with that to equal 180. So some number plus 135 equals 180. We can solve for that unknown angle by doing 180 minus 135, which equals 45 degrees. So the supplement would equal 45 degrees. Now another topic dealing with angles is what is called coterminal angles. Coterminal angles, we can actually break apart the word here. Co means with, and then terminal, that's referring to the terminal ray. Basically, they're angles with the same, so with the same terminal ray. All right, so that's your definition. They're angles in standard position that have the same terminal ray. So what we mean by that is, for example, if you're looking at a coordinate graph, something like this, and you have an angle, so here's your initial ray. Let's say you have, let's make it a 45-degree angle. So you might have this angle here, and that's 45 degrees, but we could rotate this. We can rotate this an entire 360 degrees more to get back to the same endpoint, the same terminal ray. So we can add 360 degrees to 45. That would give you 405 degrees. That angle is basically the same angle as a 45-degree angle because they have the same endpoint, the same terminal ray. So those two angles, we would consider them to be coterminal because they have the same terminal ray. We could keep adding 360 over and over again as many times as we want, and that's going to give you an infinite number of terminal angles. All right, so we can keep doing that forever. We could even go the other direction. We could go counterclockwise or clockwise. So instead of adding 360 degrees, okay, we could subtract 360. So if we did 45, so 45 minus 360, okay, what you'd do is you'd get negative 315 degrees. That would also be a coterminal angle. So in math notation, we can take your initial angle, we'll call it x, and we can add, so we add k times 360, where k could be a positive or negative number. It's any integer. So you could do 1 360, you could do 2 360s, you can add 3 360s, or as we did over here, we subtracted 1 360 or 2 360s. So we can do that in any direction. So if you were told that you had a 700-degree angle and you wanted to find a coterminal angle that is less than 360, so a positive angle that's less than 360, all we can do is just subtract 360 from this, and that would give you a coterminal angle. And that would be 340 degrees. So that would be a coterminal angle with that. If you had a bigger number, let's say you had 750 degrees, you're told to find a coterminal angle. You could subtract 2 360s, which would be 720, and that would give you 30 degrees. That would be a coterminal angle. And then if you had like a negative angle, say you had like negative 100 degrees, and you wanted a positive angle measure, a positive coterminal angle that is also less than 360, here we can add 360 to get that number. That would give you a positive 260 degrees, and that would be a coterminal angle that fits the description that we want. Now, talking more about degrees. Okay, we can break apart a degree into smaller parts. All right, so we can actually break it up into what we call minutes and seconds. And this is used in different aspects, different contexts, but one context you might see this in would be astronomy. All right, but what we do here is we use our knowledge of minutes and seconds when dealing with time, and it's basically the same thing here in this context as well. So instead of an hour with time, we have a degree. So there's 60 minutes. So there's 60 minutes in one degree, and there are 60 seconds in 1 minute. All right, and the abbreviation for this is, instead of minutes, so instead of writing 4 minutes, we can write it with this abbreviation of 4 with an apostrophe. So it looks kind of like 4 feet, but it's 4 minutes. And then if you had like 10 seconds, we can write that as 10 with 2 apostrophes, which looks like the inch symbol. So we can write it like this: 4 minutes, we have 10 seconds. So with this information about minutes and seconds, we can say that 1 minute is 1/60th of a degree, and then a second is 1/60th of a minute, or 1/3600th of a degree. So for example, if we put it all together, we might have 37 degrees, 14 minutes, and 52 seconds. We would write it like this, in this notation. And if you want to write this instead with decimals, so what we can do is 14 minutes would be 14 over 60th of a degree. And then seconds, we said that each second is 1/3600th of a degree. That can be written as 52 over 3600. So if you do that, you can get decimal equivalents. So 14 minutes, 14 over 60 would be 0.2333, and then 52 over 3600 would be 0.0144. You put that all together with the 37 degrees, that would give you 37.2477 degrees. So it's another way of expressing degree measures. So instead of writing with decimals, we could write with minutes and seconds. And then also be aware of how to use this for adding and subtracting as well. So not only do we need to know how to write in degree, or write in degree mode, like with decimals, but also make sure you know how to add and subtract as well. So for example, if we had, let's say, 10 degrees, and then you're subtracting, let's say, 3 degrees, 5 minutes, and 40 seconds. So if you're doing that, what we need to do is we need to basically borrow from the 10 degrees and put stuff here. So figure out how many minutes and seconds we have. So it's basically like borrowing with subtraction, right? There's nothing here to borrow from or to subtract from. So we borrow from the 10. So 10 degrees, we can take one of those, write that as 9 degrees. And the one we borrow, we can write that as 60 minutes. All right, well, we still need to borrow from the 60 minutes to put something over here on this last column, in the second column. So we borrow one from the 60, that becomes 59, 59 minutes. And then 1 minute is 60 seconds. So the 60 seconds goes over here. Now we just subtract. 60 minus 40 is 20. We have 20 seconds. 59 minutes minus 5 minutes is 54 minutes. And then 9 degrees minus 3 degrees would be 6 degrees. So here we have 6 degrees, 54 minutes, and 20 seconds. And then if you're trying to add things together, let's say we had 5 degrees, let's do 4 minutes, and let's do 50 seconds. And you're trying to add that with 3 degrees, let's do 7 minutes, and let's do 30 seconds. If you're adding these together, we would have 80 seconds, 11 minutes, and 8 degrees. The only thing here is the 80 seconds. Okay, there are 60 seconds in a minute, right? So we can actually convert part of this into minutes. All right, so 80 degrees would be the same thing as 1 minute and 20 seconds. So we add that with the 11 minutes. That would give you 12 minutes and 20 seconds. All right, so this would be your answer when you add those two measurements together. So we've talked a lot about degrees when working with angles, but there's also another way of measuring angles, and that is with what we call a radian. Now a radian, by definition, is the measure of the central angle subtended by an arc of length r on a circle of radius r. So what that means is, let's say we have a circle right here, okay, and the radius is some length that we'll call r. All right, so if we take that length of r, that radius, and let's create an arc with a length of r. So maybe something like this right here. So that arc length has the same length as the radius. Okay, the angle measure that creates or subtends that arc length, that is 1 radian. So that's 1 radian. All right, we can continue that if we wanted to. We can create another arc with that same length r, the radius, and that would be another radian. Now we have 1 radian, 2 radians. And if you think through this, how many radians would we have? Well, realize that this corresponds directly with the circumference, right? Circumference is equal to pi times diameter, or 2 times pi times the radius. So how many radii will it take, how many of these length r's will it take to go all the way around back to the beginning? Well, it's going to be 2 pi radii, right? 2 pi of them. It's that many of them. So we know that 1 revolution, all the way around the circle, 1 revolution, is equal to 2 pi radians. Right? It takes that many radians, that many degrees as well, to go all the way around the circle. And 1 revolution we know in degrees is 360. So 360 degrees equals 2 pi radians. And we can use this information in a moment to convert back and forth between degrees and radians. So if you want to figure out how much or how many degrees is 1 radian, we would have to divide both sides by 2 pi. So when you do that, we now have 1 radian. So 1 radian equals 360 divided by 2 pi, or 180 divided by pi. And when you divide that on your calculator, that's going to be about 57.3 degrees. So it's approximately that amount. So that's the conversion. And right here actually is the exact number. That's the exact conversion. So we're going to use that when we convert between degrees and radians. Now, one thing before we start converting back and forth is if we want to figure out the angle measure, and all we have is the arc length and the radius, we can find the angle measure in radians by simply dividing the arc length by the radius. So we take S is the arc length, divide by R, the length of the radius, and that gives you the angle measure. So for example, if the radius, let's say the radius is 8 inches, and let's say right here, this arc length is 6 inches. All right, so what we do is we do 6 divided by 8, the arc length divided by the radius, that gives you 3/4 or 0.75 radians. So that is the measure of this angle right in here. So that's the measure in radians. So now back on the topic of converting between radians and degrees. We said that 1 radian is 180 degrees divided by pi. We can use that to convert back and forth. So if you are going from radians, so radians to degrees, okay, realize radians are larger than a degree, right? Radian is like 57 degrees, I think we said. So it's larger to smaller, which means we multiply, right? So we're going to multiply by 180 over pi. Whereas if you're going the other way, from degrees to radians, so degrees to radians, we're going from a smaller to a larger unit, which means we need to divide by 180 over pi, which is the same thing as multiplying, so multiplying by pi over 180. All right, so radians to degrees, you multiply by 180 over pi. From degrees to radians, you multiply by pi over 180. And if you forget which one to use, okay, if you have to use 180 over pi or pi over 180, you could go through this thought process. Another way to realize this is, let's say we are converting the, let's say 40 degrees into radians. Okay, so if you're doing that, if you have 40 degrees, you're multiplying by some number, right? Some either 180 over pi or pi over 180, and these are in degrees, right? What we want is pi over 180 in this case, because when you multiply, you want the degrees, basically the units, to cancel. So if they're going to cancel like that, we want one on the top, one on the bottom. All right, and that's going to help you out. And now we have 40 pi over 180. We can actually reduce first. That'd be 4 over 18. And then 4 and 18 divide both by 2. That gives you 2 and 9. So we have 2 pi on the top and then 9 on the bottom. And many times we leave it with pi in there. So 2 pi over 9. That's an acceptable way of writing. You could multiply out 2 times pi and then divide that by 9 to get some decimal answer if you want. But unless specified, you can leave it with pi in there. But always make sure we simplify as far as we can. All right, let's try a couple examples on this slide. You can use this for practice. Here we have converting from 300 degrees to radians. So again, what we're going to do is we're going to multiply by pi over 180. All right, so multiply by pi over 180. We'll do it by hand here. So we know it's going to be pi over 180 because degrees, we want one on the top, one on the bottom. We want those to cancel out. And now we have 300 pi. So 300 pi over 180. We can reduce this, divide by 10, and then divide by 6 actually. It would be 5 and then 3. So what we have now would be 5 pi over 3. So that would be the same thing as 300 degrees, 5 pi over 3 radians. Let's try just one more like this, and then we'll switch to the other way, from radians to degrees. And here we're going from degrees to radians. We're converting negative 120 into radians. So again, you're going to multiply by pi over 180. That is your conversion. All right, and we know it's pi over 180 because we want degrees to cancel. So we have 120 over 180. So what we have is negative 120 pi over 180. And then we can simplify. Divide top and bottom by 10, and then divide top and bottom by 6. That gives you 2 and 3. So your answer would be negative 2 pi on the top, and then 3 on the bottom. So that would be your negative 120 degrees written in radians. Now going the other way, from radians to degrees, here we have 5 pi over 6, and that's radians. We're converting that into degrees. All right, so we know when we're converting, it's either 180 over pi or pi over 180. And again, if you forget which one to use, what we can do is realize that we want the pi's to cancel out. So we want 180 over pi because when you do that, the pi's will divide out. If you did it the other way, it wouldn't make sense, or it wouldn't work out nicely because you'd have pi squared, which is kind of a weird number to have. We want pi's to cancel. All right, that's a quick way to remember. All right, so now from here, we can simplify. 6 and 180, you can divide both by 6. That gives you 1 and 30. Now we have 30 times 5, which is 150, over 1, which is 150. So this would be 150 degrees. So we've learned how to convert between degree and radian measure. What you see here is called a unit circle. And what this is it's a way to help you remember the conversions of very commonly used degree and radian measure. So this is specifically for the special right triangles, for the 30, 60, 90 triangle, or the 45, 45, 90 triangle. And here, what we're looking at is we're starting at 0 degrees, so right here. So this is, think of like a coordinate graph. This is the origin. And right here is the first ray, the initial ray of your angle. And then we're going from that spot, we're working around counterclockwise this way in the direction of this arrow. All right, so there's a lot of information here and it can be overwhelming when you first look at this. But there's a pattern that's going to really help you just come up with these really quickly. All right, so working with degrees we're very comfortable with using degrees typically. All right, so we see 30, 45 degrees, 60 degrees, 90 degrees, etc. But the radian measure is more new. So looking at the radian measure specifically, here at the 30-degree angle, the conversion of that would be pi over 6 radians. And every 30-degree increment is going to be another pi over 6 degrees. So ignore the 45 degrees and the 90 degrees and the 135. Ignore those increments of 45 degrees for the moment and look specifically at the increments of 30 degrees. So here we have 30 degrees, 60 degrees, 90 degrees, 120, 150, 180, etc. So if you remember the simple fact that 30 degrees is equal to pi over 6, okay, we can just increase with every 30 degrees, increase the radian measure by pi over 6 as well. All right, so when you go to 60 degrees, we have 2 pi over 6s. So we just simply have 2 pi over 6, which would reduce to be pi over 3. And that's how we got the radian measure. 90 degrees is 3 pi over 6s. It's 3 30-degree measures. So we have 3 pi over 6, which reduces to give you pi over 2. And that's what we have right here. And that would continue all the way around. So if we go to 120 degrees, notice that's 4 30-degree increments. So that's 4 pi over 6s. And then we can reduce that to get 2 pi over 3. And that's how we get this radian measure. And then 150 degrees, that would be 5 30-degree increments, 5 30 degrees. So we do 5 times pi over 6 to get 5 pi over 6. And that is the radian measure. And then 180 degrees, that would be 6 increments of 30 degrees. So we have 6 pi over 6, which would reduce to give you pi over 1 or just pi. All right, so also notice that when you go all the way around the circle, we said that one complete revolution is 360 degrees or 2 pi radians, which means that 180 degrees must be half of that. So 180 degrees would be 1 pi revolutions. All right, we can use that to help us with getting these other degrees down here, the 210, the 240, 270, etc. Because instead of trying to think through, or try to count by pi over 6s, starting with 0 degrees, we could just pick up right here, realize that this is 6 pi over 6s. All right, and then so the next one would be 7 pi over 6 right here. Then we have 8 pi over 6, which is 4 pi over 3. Then we have 9 pi over 6, which is 3 pi over 2. 10 pi over 6, which reduces to be 5 pi over 3. Then 11 pi over 6, which is just 11 pi over 6. And then 12 pi over 6, which reduces to give you 2 pi for 360 degrees. All right, so that's the pattern with the 30-degree increments. And now looking at the 45-degree increments, 45 degrees, all you have to remember is that 45 degrees is the same thing as pi over 4. If you realize that fact, you can do the same process by counting by pi over 4 to get to the next 45-degree increment. So 90 degrees is 2 pi's over 4, which reduces to be pi over 2. And then 135 degrees is 3 pi over 4, which does not reduce. You just have 3 pi over 4. And then you have 4 pi over 4, which is 180, which is equal to just 1 pi. Then you have 5 pi over 4 is the next increment. And then 6 pi over 4, 7 pi over 4 is 315 degrees. And then 8 pi over 4 would be 2 pi over here. So again, there's a pattern to all of this. So yes, there's a lot of information on this unit circle, but if you remember the pattern, you can quickly derive those very commonly used degree and radian measures. And now we're going to switch gears again and talk about arc length. All right, so we mentioned a couple slides ago that we could find the angle measure in radians simply by dividing the arc length s by the radius of the circle. Now, if we wanted to, we could rearrange this formula, multiply both sides by r. That would give you s, the arc length, equals the radius times theta. So what this does for us is this gives us a formula to solve for arc length, because s is the arc length. So all we do to find the arc length of on any circle is we take the radius, multiply by theta. Just keep in mind that theta, this angle measure, okay, that's got to be in radians. Okay, if it's not radians, this is not going to work. So here's an example where we're trying to find the arc length of an arc on a circle with radius of 4 inches and a central angle of 25 degrees. Alright, so again, we can use our arc length formula. So arc length equals your radius times theta. Radius is given to us as 4 inches. So we have 4 inches times theta. But remember, theta, this angle measure, must be in radians. So we must convert 25 degrees into radians. So to do that, we have to multiply by our conversion. So either pi over 180 or 180 over pi. We know it's got to be pi over 180 because the degrees here and here, we want those units basically to cancel. So we want it set up like this, and we can simplify, divide top and bottom both by 5. That would give you 5 right here, and then this would give you 36. And so that would give you 5 times pi over 36. That would be your theta value. So now we just put that together. Arc length S equals radius, which is 4, times theta, which is 5 pi over 36. Now 4 and 36 can divide. You're left with 1 and 9. So we have 5 times pi over 9. And we could leave it like this, but since we're dealing with an arc length, we probably don't want pi in there. We're going to want to multiply that out. So if you do 5 times pi, then divide by 9, that gives you a number of 1.745. And you could round that if you want to about 1.7, and the units would be in inches. That is the arc length. So your solution for this problem would be that the arc length would be 1.7 inches in length. Now, on the topic of arc length, there's a trick we can use that may be helpful in certain situations where, let's say, for example, you have an astronomer. So you have an astronomer here on the Earth. So he's down here, and he's looking at, let's say, a star cluster. So star cluster, a bunch of stars up here, off in the distance, and let's say that when he's looking up there, he's trying to figure out how wide the star cluster is. So he wants to know this length. Okay, so it's a straight line. I didn't really draw it very straight, but it's supposed to be a straight line. Trying to figure out what is this length off in the sky, like how far apart are the stars. All right, well, when dealing with astronomy, right, the distance is going to be incredibly large. So the radius, the distance from here all the way out to here is going to be very large. It's a very large number. Okay, and the radius, if we go to the other side here as well, it's going to be that same large number. Okay, so what we have is 2 radii. We have an angle right here, and the radii are incredibly large. This degree, this angle measure, is going to be incredibly small. And even though we're trying to find a length, all right, we're trying to find the length from here to here, okay, because it's such a small degree measure and such a large radius, we can approximate that length by actually trying to find the arc length. So we're trying to find the straight line length, but we can approximate it by using the curved arc length. So we can use, again, the formula of arc length equals the radius times theta, the angle measure. So let's say that the radius is 237 light years. All right, so that's Ly, light years, with capital L, I guess, light years. And then let's say the degree right here is 3.5 degrees. What we can do is we can find the arc length by taking the radius, multiplying it by this angle measure. So if you did that, you would have radius would be 237. Theta, we need to convert degrees into radians. So we do take the 3.5, we multiply that by pi over 180, and that's going to give you the arc length. And when you do that, you're going to get 14.48. So with this example, we can conclude that this arc length here, which was the distance across this star cluster, is 14.48 light years across. So again, that's a technique we can use to find an arc length when the degree is very small and when the radius is very large. Next, we're going to talk about linear and angular speed. So we're still talking about circles, all right? And with the linear speed, what that is the speed with which a certain point on the circle will reach another point. So if you have a circle here, and you have a point, say, right here, we're trying to figure out the speed with which that point is traveling around to, say, another location over here. So when it's rotating, what is the linear speed? So when you're doing that, when you're trying to calculate that speed, we need to know the arc length. So this length from here to here, that is your distance. All right, so we take the arc length and divide it by the time it takes to travel that distance. So here v is velocity. That equals your arc length divided by the time it takes to make that happen. And remember, arc length can be calculated by doing the radius times the theta, the angle measure in radians. Now, angular speed is the rotational speed. So we want to know if you're starting here with this ray, and then you're ending up here to this ray, let's say that's some angle measure, we'll call it theta, how quickly is it rotating that number of degrees? So instead of a length divided by time, it's going to be the angle measure divided by time. And here we use the Greek letter omega. It looks kind of like a W. So it looks kind of like that if you write it out. That equals the theta, the angle measure, divided by the time. So let's take a look at an example where we are using angular speed conversions. In this example, we have the idle speed of a car's engine was about 700 revolutions per minute, or RPM. Find the angular speed in radians per second. So what we can do is we can write out what we are given. So we have 700 and then revolutions per minute. We'll write it as a fraction. And then what we're going to do is we're going to try to convert this into radians per second. One way we can convert is by using a process called dimensional analysis. And we can use it for any sort of converting. It doesn't have to be angular speeds, but it does work here as well, where we know that one revolution is 2 pi radians. That's the number of radians to go all the way around the circle. So we can write that. We write 1 revolution is equal to 2 pi radians. And I chose to put revolutions on the bottom and radians on the top because if revolutions on the bottom, notice that these units would cancel. So what you have left now is radians per minute. Radians on the top, minutes on the bottom. So we're getting closer. We have radians per minute. We need radians per second. So the radian part is good up here. Now we need to work on the minute part. So how do we convert minutes to seconds? Well, 1 minute is equal to 60 seconds. So we can write that out like this. And we chose to put minute on the top because if minute is on the top, that cancels with minute down here on the bottom. So now what you have left is radians on the top, seconds on the bottom. So we have radians per second, which is what we want. So now just multiply across on the top and on the bottom. 700 times 2 pi is 1400 pi. That's on the top. And on the bottom we have 60 seconds. That's radians on the top. So 1400 pi radians over 60 seconds. And then we can simplify this. So we can do divide top and bottom by 10. that gives you 140 over 6. Divide top and bottom by 2, that gives you 70 over 3. And that would work. We have 70 pi over 3, and that's radians per second. And that would be your answer. And if you wanted to, you could multiply out the pi to get some decimal answer, but this would be okay to write it like this. Let's take a look at one more example, and here we are trying to find the linear speed. So in this example, we are given a clock. So we have a clock, and it says the second hand of a clock is 10.2 centimeters long. So that means the radius, basically, the second hand, is 10.2 centimeters. And we're trying to find the linear speed of the tip of the second hand in centimeters per second. So to find the linear speed, we need to know the circumference. So here we can do circumference equals pi times the diameter. All right, so diameter is 10.2. And so the diameter, radius is 10.2, diameter would be 20.4. So we have pi times 20.4. And that would give you 64.088. All right, so that would be in centimeters. That's the circumference. All right, so that is the distance. And then we need to figure out how long it takes to travel that distance. So we know velocity, linear speed, is equal to the arc length divided by the time, right? Arc length in this case is we're going all the way around, which would be the entire circumference, which would be 64.088. The time it takes for the second hand to go all the way around would be 60 seconds. All right, so we have 60 seconds is our time. So now we have centimeters per second, which is what we want. So all we do is we divide that number by 60, and when you do that, you're going to get 1.068, and that would be centimeters per second. So the linear speed of this second hand on the clock would be 1.068 centimeters per second. And that concludes our lesson for today. We will see you next time.